Hello and welcome to Honors Calculus. In this video kicking off lesson 0 on logic and proof, we're going to be talking about sets of numbers. So without further ado, I'm going to get my head out of the way so that you can read my notes, and let's get started. Many of the definitions we'll be talking about here you should already be familiar with. For example, a set is a collection of objects which we call the elements of the set. And when we are talking about sets, we can build up a set using roster notation. For example, set A might be the set containing the numbers 1, 2, 3, 4, and 5. And roster notation works really nicely when we have relatively small sets. If we have a larger set, we're going to want to use something like set builder notation. Set B might be the set of all x such that 3 is less than or equal to x is less than 5. So all of the values between 3 and 5, including 3, not including 5. For our purposes in this course, one of the important tools we're going to be using in working with sets is the element of operator. So for example, if we look at our sets here, we can see that the number 4 is an element of set A, and 4 is also an element of set B. We can see that 5 is an element of set A, but 5 is not an element of set B. So the element of operator lets us talk about things that are in sets and things that are not in sets. It kind of looks like a stylized letter E. When we're talking about sets and we're talking about elements of sets, it makes sense to mention a pretty popular set, a set which has no elements whatsoever, the empty set. And the variable we use to denote the empty set is an O, letter O, with a slash through it. And this is the set which has a roster with absolutely no elements in it whatsoever. When I'm talking about the empty set, I always have to mention one of the common mistakes I see students make is mixing up what's going on where. Right? This symbol of a circle with a slash in it is the variable name of the empty set. Just like we use the symbol pi to represent the circle constant 3.14159. We use circle with a slash through it to mean the empty set. So if you put a set and you put that inside, this is the set containing the empty set. This is a set that has one thing in it, that one thing being the empty set. There are places where the set containing the empty set is a very important tool. We're not going to be looking at any of them in this course. So I bring this up specifically to mention that you should never talk about the set containing the empty set when we're discussing things in this course. We will be talking about the empty set a lot. We will be talking about sets containing various things a lot. We're never going to mention the set containing the empty set. All right. Now it's time to get interesting. You have almost certainly come across the definition of the natural numbers in the past. You may or may not have seen this symbol. It is a blackboard bold, or sometimes called double stroke N. It's the letter N with an extra bar in it. And that's the symbol that we use to represent the natural numbers. And you've probably seen this definition in the past of the natural numbers being the set containing 1, 2, 3, and dot, dot, dot. And for the purposes of an algebra class, for the purposes of an arithmetic class, dot, dot, dot is good enough. We understand that the natural numbers are the counting numbers, the numbers that you would use when trying to count. But for this purpose, for honors calculus, that is no longer going to be good enough. We need to clearly define what we mean by dot, dot, dot. And we do that using what's called the successor or the induction operation. So instead of just talking about the natural numbers as this dot, 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 we're going to define the natural numbers by two properties. All right, I've run out of page, so let's move that onto the next page to work things out a little bit nicer later on. Right, we start off by defining that the identity 1 is in the natural numbers. And the second property we want to use is that if little n is a natural number, then n plus 1 is also a natural number. Using these two rules, right, we start with 1. Since 1 is in there, then that means 1 plus 1, which is 2, is also a natural number. Since 2 is a natural number, 2 plus 1, which is 3, is also a natural number. Since 3 is a natural number, 3 plus 1, which is 4, is also a natural number. And we just keep repeating this indefinitely. And in theory, if we go long enough, we get all of the natural numbers. This is our definition of the natural numbers. It's much clunkier than just 1, 2, 3, and so on, but it is exact. It tells us exactly what the natural numbers are and how they work. And that's really a microcosm of what this course is going to be all about. We want to try to find ways to put rigorous footing on all of those hand-waving arguments that you are very familiar with. We've started with the natural numbers. Now that we have those, we can build up a nice rule for the integers and the rational numbers. That will be the big thing in this lesson. In lesson 2, we'll go on and start talking about what it takes to put the real numbers on a solid footing, which is unfortunately going to be an awful lot more work. And then we'll go on from there. So keep that in mind as we go through this course. The whole idea is to take these definitions that you're familiar with and put them on solid footing so that we can really use them for other things later on. talking about sets, another thing that we commonly look at are the set union and set intersection. The union of two sets A and B is the set of all elements X such that either X is in A or X is in B or both. Set intersection, A intersect B, is the set of all X such that both X is in A and X is in B. Again, the definitions that you're familiar with. Union is anything that's in at least one of the two sets. Intersection is anything that's in both of the sets. A little bit more carefully worded than you're probably accustomed to. All right. Quick warm-up just to make sure that you're familiar with those ideas and you remember this idea of union and intersection. If we have set A, which has the elements 1, 2, 3, 4, and 5, and we have set B, which has the elements 2, 4, 6, and 8, then the union of these two things, A union B, is anything that is either in A or in B or both. Right? So 1 is in A, that's good. 2 is in both of them, that's good. 3 is in A, that's good. 4 is in both of them, that's great. 5 is in A. 6 is in B. We don't have a 7. We do have 8 in B and nothing else. So A union B will be 1, 2, 3, 4, 5, 6, and 8. A intersect B asks us for the list of elements that are in each of these two things. So 1 is in A but not B, that's not good enough. 2 is in A and also in B, that works. 3 is in A but not B, that's out. 4 is in both of them, that's fantastic. 5 is in A but not B, no good. 6 is in B but not A, no good. 8 is in B but not A, also no good. And there's nothing else in either of them. So there is our intersection. All right. Now let's just go down to the clean page now. Next operation on a set, or I guess a relationship on sets, is the subset. The upside down letter A, remember, is a shorthand of for all, or sometimes for every. So A is a subset of B. I jumped right to that. I forgot to give you the shorthand here. IFF, an incredibly frequent abbreviation in mathematics. Means if and only if. So A is a subset of B if for all X in A, X is also in B, and if for every X in A, X is also in B, then A is a subset of B. So if you have one side of this rule, you automatically get the other. If and only if says the implication works both ways. When you have one side, you get the other. When you have the other side, you get the first one. Which is important in a lot of mathematical definitions. Sometimes we will be given information about a subset and use that to derive some other piece of information by using the definition. Sometimes we will do some work, get to this definition, and use that to say, and yeah, we have a subset. And with that, we get to the first theorem of the course, which is kind of a strange theorem. For any set A is a subset of A. The value in mathematics of a theorem is that a theorem is establishing nothing new. The purpose of a theorem is to take things we already know and show that some other result must also be the case. So by using just our definition of a subset, it must be the case that for any set A is a subset of A. That's not a new rule about subsets. That's something that is forced to happen because of the definition we've already had. All right. And to prove that, we get one of the stupidest lines in mathematics. If x is in A, then x is in A, obviously. But that's what it takes. If we take any value of x in A, we get that x is a value in A. And that's the definition of a subset. If x is in A, then x is also in B. Just a little bit weird because it's the same thing in both places. And when we conclude a proof in mathematics, we typically put a tombstone symbol or a QED symbol. I'm partial to a square that gets filled in or kind of squiggled in, depending on how lazy I'm being. And there we have one nice result on sets. Right, that takes us to the next theorem, which is even goofier. For any set B, the empty set is a subset of B. Right? That's a very strangely worded result, but it is a result and it is valid. Bringing this result up early lets me talk about an idea called a vacuously true statement. One of the pitfalls of mathematics is that we need to be able to say that any statement we come up with is either true or false. We call this the law of excluded middle. Every statement that we can possibly come up with must either be true or be false. So in this particular case, we say that this statement is true because trying to say that it's false gives us complete nonsense. Right? What would it mean for the empty set to not be a subset of B? Right? Well, A is a subset of B if every element in A is also in B. So that means that A is not a subset of B if you can find an element in A that is not in B. So for this statement, we have to find an element in the empty set which is not in B. But how do we find an element in the empty set which doesn't have any elements? That doesn't make any sense. That's nonsense. That's garbage. And so that's where the issue comes up here. This statement is vacuously true. Since there are no elements in the empty set, then there can be nothing in the empty set which is not in B. Which means that there's no way to say that the empty set is not a subset of B. Sorry about that. Subset, not element of. Right. Take a minute and digest that idea before we continue on. Pause the video if you need to. Because that's a very abstract proof. Because there is no way of saying that the empty set is not a subset of B, the only thing that leaves is that the empty set is a subset of B, and so we'll just accept it. That's difficult to do, but the math checks out. Playing around with sets just a little bit more here. I'm going to trigger someone's OCD by creating set C, which contains red, orange, green, blue, and yellow. And I'm going to create set D, which contains the colors blue, yellow, red, black, white, and brown. And just to make sure that all of this discussion of sets has made sense for you, I would like you to try to find C intersect D and C union D. Take a few minutes, play around with that, submit your results, and I'll see you in the next video.